Okay, this is the last new material of a semester. There will be one more video recorded after this one to be a review of the practice final exam, and that'll be early next week. And so let me make a note of that here. So um, practice final exam review. And the practice final uh, is untimed, and you're given 100 attempts, just like of test 2. Posted in WebAssign. Time versions, I've not posted those yet as of now, but I will do the same thing as I did with test 2, put out the 5 time versions of the practice final for you. That'll be done sometime this week. So as far as source material for today's lecture, so we're continuing with 7.3 in the textbook, 4.4 in my notes, so what's at the very end of my notes. And what it's all about today is solving differential equations in which the right-hand side is a function that is piecewise defined, so it can have discontinuities. So last time we learned how to write such functions in terms of unit step functions, also known as Heaviside functions, and then from there take the Laplace transform of them. So now we can take advantage of that knowledge for solving differential equations that include such functions. So all I'm going to do is step through a few examples so you'll be ready to do the same thing on homework or the final. And I also want to mention, I think I had not mentioned this before. Okay. So final, whoops, sorry, not here. So the final exam is not comprehensive. If that was the plan, but in light of the current situation, I've decided to narrow its scope, cover only the material on Laplace transforms. So problems we taken from homework 7.1, 7.2, 7.3. So I've literally chosen certain problems from those homework assignments with different numbers, randomized numbers, of course, and put those on the final. So if you can handle these homeworks and also do these problems efficiently, then you'll be fine for the final exam. And as far as time goes, so you get 2 attempts like you did for the for test 2. 4 hours total. Now, what I may do instead, I'll have to figure out how to set this up, but the idea is I want to have you be able to take at least 2 hours on a given attempt. So 4 hours is a longer time span than the 2.5 hours I was given last time. So what I'll probably do is set up 2 separate finals, 1 attempt each. So then, and then I'll take the best one. So 2 hours each. So it'll have to be done as 2 separate assignments within WebAssign. But I can easily set up a gradebook so that it'll just take the best one of those 2. So whichever final, if you don't use both attempts or one is better than the other, it'll the lower one will automatically be dropped. Okay. It'll be opened Monday, May 11th. That is finals week. To Thursday, May 14th, 11:59 p.m. So it just runs through all of finals week. Okay. So now, for the last material that will be included on this final, I'll work some examples for you. So we have this differential equation, second order, y double prime plus y is equal to some given function g of t, and that function, in this case, is defined to be 1 for t up to 3 pi and equal to 0 after that. And then we also have initial conditions, y0, 0, y prime of 0 equals 1. Okay, so what we do, like before, is take the Laplace transform of both sides. Okay, audio recording got interrupted. Let's hope that doesn't happen much more. Okay, so here I'm taking a Laplace transform of both sides of this equation. So what we end up with is s squared y of s minus y prime of 0, which is 1. And then normally subtract off s times y of 0, but y of 0 is 0. So that's all we have there. And then plus y of s for the y term. And now on the right side, we need to take a Laplace transform of this function here. So the way that works is at t equals 0, we just have a function equal to 1. So the Laplace transform of 1 is just 1 over s. So that accounts for the 1 part. But now for discontinuity, we have to, at t equals 3 pi, turn off 1. And then we don't turn on anything else because the function is equal to 0 after that. So if I subtract off, okay, what I need to write down here or type in, what am I transforming? So actually what I'll do is, I'll do that here also. All right, so I'm turning on 1, and then what I'm turning off is also 1. So that would be unit step function at t minus 3 pi, because I'm turning off at 3 pi. And whatever function I'm turning off gets multiplied in here. But what I'm turning off is 1, so I don't need to include anything else. All right, so then the transform of that, 1 over s for this term, and then the transform of this unit step function is equal to e to the minus, and then whatever value is being subtracted here, 3 pi, times s, times the Laplace transform of whatever function is multiplying the unit step function. Well, that function is 1, so we again have 1 over s. Okay, so that's the Laplace transform of the right side. So because we have 1 at first, we have a Laplace transform of 1. Then we're subtracting off this step function at time 3 pi times the function we're turning off, which is 1. And then that describes everything that's going on here. So now we have the differential equation transformed. So now what we need to do is solve for y of s. So I need to factor y of s out of whatever terms we have here on the left side. So I'm going to have s squared plus 1. And then I have this term, a minus 1, that gets moved to the other side. So my denominator is going to be whatever's multiplying y of s, s squared plus 1. Okay. Now, what's something went wrong here. Oh, okay. So now what I include in these brackets is everything that was already here. So I'll just copy and paste that. And then this minus 1 gets moved to the other side. So I'll have a plus 1 there. Okay, so to recap, first, move this minus 1 to the other side, it becomes a plus 1. So now we have everything you see in the square brackets. Then divide by whatever's multiplying y of s on the left side, s squared plus 1. So that's the denominator here. Okay, so now if I distribute that 1 over s squared plus 1 through, then I'm going to have 1 over s squared plus 1 times everything had a 1 over s in it, because I have that down here. I'm factoring 1 over s out of the first two terms anyway. So I have 1 minus e minus 3 pi s. And then the other part I have is just 1 over s squared plus 1. Okay. Now, this is a Laplace transform my solution. What I need to do now is inverse transform all of this. Now, that part, the last term, is going to be pretty straightforward. We'll get to that at the end. It's this part that's going to take more work. So we need to carry out a partial fraction of 1 over s squared plus 1. So that's going to be equal to a constant over s plus, now the rest of the denominator is s squared plus 1. Now normally with a quadratic we would factor it, but this is called an irreducible quadratic. If you factor this, you'd get complex numbers, either s plus I and s minus I. But we want to avoid dealing with complex numbers. So we leave this quadratic as is, unfactored, but then up top you must put a linear function instead of just a constant like we normally have. That's something to keep in mind, is that if your denominator includes this kind of irreducible quadratic, one that cannot be factored without using complex numbers, then you must put a linear function in the numerator for that term in your partial fraction decomposition. Okay, so now, and you get side, and on the right side we get a s squared plus 1 plus bs plus c times s. Okay. Now, normally what you do is you find values of s to substitute in here to get the values of your constants, your a, b, and c. And you can certainly do that in this case. The trouble is it's harder to find convenient values of s that'll work. Certainly s equals 0 would help, because it would wipe out this whole term. But since there are no other obvious values of s you can choose, you can really choose whatever you want. Any 3 distinct values will work, and you get equations that you would solve for a, b, and c. Or another way you can proceed is you can just expand the right side and match like powers of s. So what are your s squared terms? I have as squared plus bs squared. So I have a plus b s squared. And then for terms that are linear in s, I have c times s. And then as for constant terms, I just have, the only constant term I have, we have s throughout this, so we can forget that. We just have a. All right. Wait, not here. Down here. So that's another way to proceed. Either way would work. It's up to you. So here we have a quadratic in s. Here we have just a constant function. So we must have a plus b. C equals 0. And from matching these terms, we get a equal 1. So C and A are determined. Now I substitute this value in here to get B. So B turns out to be equal to minus 1. So now I can take my values of A, B, and C and substitute them up here and use that decomposition in here. So what is that going to give me? Going on to a new page. Okay, so 1 over s equals 1 is equal to, all right, a over s, so that's 1 over s, minus s over s squared plus 1. So filling in a, b, and c up here gives me this. So now what I can do is take this decomposition and move it up here. So what does that give me? Y of s is equal to so we have this decomposition here, which I'll just copy down here. Okay, times 1 minus e minus 3 pi s. And then if I go back, I still have this term. Okay. Now, what I'd like to do is multiply this out so I get terms that I can readily inverse transform. So just multiplying this out, I get 1 over s. Okay, then I have minus s over s squared plus 1. Then I have minus minus 3 pi s 1 over s plus e to the minus 3 pi s over s squared plus 1. And then I still have this straggler term here. Okay. So multiplying all this out gives me this. Now, to inverse transform y of t, well, the inverse transform of 1 over s is just 1. This s over s squared plus 1, that is minus cosine of t. And then over here, what I have is 1, but because multiplied by e to the minus 3 pi s, that's going to be multiplied with a unit step function. So that's going to be minus unit step function of t minus 3 pi. Over here, I have this is a transform of cosine, but that also is multiplied by a unit step function. So that's going to give me plus unit step function t minus 3 pi times cosine, but not of t, it's t minus 3 pi. So don't forget, when you have something you're inverse transforming, if it's multiplied by this kind of exponential, e to the minus a constant times s, go ahead and inverse transform this, which gives cosine t, but then you must shift by whatever value we have here. So it's always e to the minus a constant times s. That constant gets subtracted from t here. That happened too in this term, but it's a constant function. A shift of a constant function is still that same constant function, so nothing needed to be done down here. The only thing left is this term. That is the 1 over s squared plus 1 is a transform of sine t. So now everything is inverse transformed. We could stop here. One thing that could be done to simplify is that cosine of t minus 3 pi by trig identity for a cosine of a sum is cosine t cosine 3 pi plus sine t sine 3 pi. Well, sine of 3 pi is 0. Cosine of 3 pi is the same as cosine of pi by periodicity. That's minus 1. So that's equal to minus cosine of t. So what you could do is replace this cosine of minus cosine t. Again, not really a big deal, but it's one way to get these solutions in a slightly simpler form. And that's it for this example. So you take the transform of your right-hand side function after your left side of the equation, and because it's piecewise defined, you write it in terms of unit step functions, and then you do a similar algebra working with the Laplace transform before you inverse transform it. But any terms that have this exponential, the result of the inverse transform is multiplied by shifted unit step functions, and don't forget to shift the rest of it as you inverse transform as well. Okay. Now, let's see. I'm going to do another example. So the problem we will solve is y double prime plus 4y is equal to I'll fill in the right side in a little bit. First initial conditions, y of 0 equals 0, y prime 0 equals 0. Okay, so right hand side function is equal to sine t for t greater than or equals 0, and then is equal to 0 actually, I'll write this way. T from 0, okay, up to 2 pi. And then after that, for t greater than or equal to 2 pi, then the function is equal to 0. Okay. Now, and I'm going to call this function g of t. All right. So, what we should do first is write g of t in terms of unit step functions. So g of t is equal to, starting out, just plain old sine t. Then, at t equals 2 pi, we need to turn we need to turn sine t off. So that's equal to unit step function of t minus 2 pi Now, we fill in 2 pi here because that's a time at which we're turning this off. We put in a minus because we're turning off. And what is it we're turning off? Sine t. Okay. So sine t is effectively switched on at t equals 0, switched off, subtracted off at t equals 2 pi. But we need to write this term as a function of t minus 2 pi. So if I write it this way, sine t minus step function, this kind of thing I was doing last time, t minus 2 pi sine, if I write t minus 2 pi plus 2 pi. So now I'm going to group these two terms together, t minus 2 pi. All right. Now, what you could do here is expand this using a trig identity, but in this case, it's not really necessary because, as you should know, sine, like cosine, is 2 pi periodic. So sine of anything plus 2 pi is equal to sine of that something. So I can just remove this, and now we're done. So it's important to get this in terms of same arguments as passed to the unit step function. So not as a function of plain old t, but a function of t minus whatever is being subtracted here. Okay, so now it's in a form where we can carry out the Laplace transform. Okay, so what we get is s squared y of s for the second derivative. And then there's no initial data here, so that's the only term we get from the second derivative, plus 4 y of s from this term here is equal to a transform of this. Well, a transform of sine is, as we saw before, 1 over s squared plus 1. And then we need to take a transform of this term. Well, what we use is the rule for function being multiplied by a unit step function. So we transform this function unshifted. So transform of sine t times what we get from the step function, and that's going to be equal to e to the minus 2 pi s. And we have a minus here because of a minus right here. Okay. So the rule to use, or the two that I used here, transform of sine bt is equal to b over s squared plus b squared, and then transform of a unit step function t minus c times some other function also of t minus c. That's why it has to be written in this form to correspond to this, so that this rule will apply, and it's equal to e minus cs times the Laplace transform of the unshifted form of this. So what I did here, I had u of t minus 2 pi, sine of t minus 2 pi. I take a transform of sine t, that gives me this. And then to account for the unit step function, then it's e to the minus cs, where c is 2 pi in this case. And then because this whole thing is subtracted, it's subtracted here also. So now this is the transform that I will work with. I just need to rearrange to solve for y of s. Okay, so on the left side, I'm going to factor out y of s. It leaves me with s squared plus 4. So now I can divide by that. So what I have is 1 over s squared plus 1, s squared plus 4, and then 1 minus e minus 2 pi s. Okay. So now, as far as partial fraction decomposition goes, I need to decompose this. All right, so this whole fraction here up here. AS plus B over just S squared plus 1. And then the other fraction, I have CS plus D over just S squared plus 4. So both factors are irreducible quadratics. That's why in both terms I must have linear functions rather than constants. Okay, then multiply through by denominator. So you get 1 on the left side. That's equal to AS plus B, S squared plus 4 plus CS plus D times S squared plus 1. Next, multiply everything out. So what you get is, after multiplying everything, you have A plus C times S cubed, and then I have B plus D S squared. So like here I have BS squared and DS squared. Here I have AS times S squared, that's AS cubed. Here I have CS times S squared, that's CS cubed. So that's where these terms come from. Then I have plus 4A plus C times S, because I have 4AS, and then CS times 1. And then the constant term is 4B plus D. So now I have everything grouped by powers of S. So then I could just equate all the coefficients. I only have 1 on the left side, so I must have A plus C equals 0, B plus D equals 0, 4A plus C equals 0, and 4B plus D equal 1. Okay. Now, getting A and C is easiest. So from here I have C equals minus A. So if I use that in here, C equals minus A, I get 3A equals 0. So A is 0. From here, C is minus A, so C is also 0. What about B and D? So here I have D equal to minus B. So if I use that in here, I have 3B is equal to 1. So B is 1/3. From here, D is equal to minus B. So I get minus 1/3. Okay. So now I can take all these values and put them back up here, and then use this decomposition up here for y of s. So filling in these constants, what I get is y of s is equal to okay, so I have 1/3 1 over s squared plus 1 minus 1/3 1 over s squared plus 4. Okay, now for purpose of inverse transforming, I should expand all this so I can focus on each term individually. Okay, so what I will do is copy and paste this. Now, for inverse transforming, first these two terms that don't involve a unit step function. So y of t. So here I have 1/3. That's just sitting there. And this is the transform of sine t. And then here I have 1/3. And then this is a transform. You think, oh, this is a transform of sine 2t, except for one thing. This term is not, this factor right here, 1 over s squared plus 4, is not a transform of sine 2t. If we go back to this rule here, the transform of sine 2t is 2 over s squared plus 4. So to take that into account, what I like to do to cut down on mistakes is up here, since I wanted 2 for a transform, I'll put a 2 up there. I just have to compensate for it by adding an extra factor of 2 down there. So really what I have is minus 1/6 sine of 2t. And I'll do the same thing up here. So 1/6 and then 2 over s squared plus 4. So it fits nicely. So what I have here, I know the transform of this because it's the same thing that I have over here. But I have to multiply when I inverse transform by unit step function. So I can have minus unit step function of t minus 2 pi. And the same inverse transform that I had before, but don't forget to shift it. Or as a function of t minus 2 pi rather than just t. 2t minus 2 pi. Okay, so wherever you see t, it's replaced by t minus 2 pi. So actually, there is a slight mistake I just realized in the notes. I have note parentheses here, 2t minus 2 pi. It happens to be equivalent just because of a periodicity of sign, but that is a mistake that I ought to fix. So if I multiply this through, the idea is t gets replaced by t minus 2 pi. So I really have 2t minus 4 pi. But because sine is 2 pi periodic, for my final answer, I could just replace these arguments by just t in this case, and 2t in this case. And then I'm done. In the notes, I make this combine this into one term, do some factoring, but that's really not necessary at this point. It can just be left like this. In WebAssign, when you solve these problems, it has you enter this part of the solution, the part that's not multiplied by a unit step function, in one box. It has you enter the shift in another box, and then whatever that's being multiplied by a unit step function, that gets entered into a third box, just so you know how answers are supposed to be entered in WebAssign for these kinds of problems. Okay, so that's it for this example. I have one more. Okay, so the problem is y double prime plus 3y prime plus 2y is equal to some function g of t, which is defined to be is equal to 1 for t up to 10, from 0 to 10, and then for 0 for t greater than or equal to 10. And then we have initial conditions, y 0, 0, y prime 0 equals 0. Okay. Now, first thing to do, write g of t in terms of unit step function. So g of t starts out being 1. So whatever is being turned on at t equals 0, just go ahead and put it in there. And then I will turn off 1 at t equals 10. Um, so, uh, so I have a step function at t minus 10 because we're turning off at time t equals 10, multiplied by a function you're turning off, which in this case is 1. Now, I can take the Laplace transform of both sides of the equation. So for second derivative, I have s squared y of s. There's no initial data, so there's no other terms. Then 3s y of s for the first derivative. Normally we subtract off y of 0, but no need in this case, it's 0. And then 2y of s is equal to the Laplace transform of this function, which is equal to 1 over s for the 1. And then for this part, because of the unit step function, we have e to the minus 10s times whatever function is being multiplied by, which is 1. We transform that. That gives us, again, 1 over s. All right. Now we need to isolate y of s by itself on one side of the equation. So we get 1 over s squared plus 3s plus 2 times over s minus e minus 10s over s. Okay, but now what I'm going to do is I'm going to factor out a 1 over s from all this. And then this, s squared plus 3s plus 2, that factors nicely. So that would be s plus 1 and s plus 2. And then we still have 1 minus e to the minus 10s. But now we need to carry out the partial fraction decomposition of this. So we get two factors from the left side of the equation, this one from the right side. So it's important to put all those factors together. All right, so what we have is 1 over s plus 1, s plus 2, and that's equal to constant over s plus constant over s plus 1 plus constant over s plus 2. We have no irreducible quadratics in this example, just linear factors, so we only need constants in our numerators. All right, multiply through by the denominator, we get 1 on the left side is equal to a times whatever is not below it. So s plus 1, s plus 2, plus b, s plus 2, plus c, s plus 1. So in this case, we have convenient s values that we can substitute in to get our coefficients. So we can substitute in 0 and minus 1 and minus 2. And what do we get for our constants? If we plug in s equals 0, that wipes out these two terms. So I get 1 is equal to a times 1 times 2. So a turns out to be equal to 1/2. Stupid thing. Okay. Then I substitute s equal to minus 1. That wipes out this term and this term. So I get b times minus 1 times 1. So b equals minus 1. And when I substitute c equal to minus 2, that wipes out, or sorry, not c. I'm sorry if I said c earlier. We are substituting s equal to those values. So substituting s equal to minus 1 wipes out that, gives us b equal minus 1. Substituting s equal to minus 2 wipes out the a term and the b term. So I have c times minus 2 times minus 2 plus 1 is plus 1. So I have 1 is equal to c times a positive 2. So c turns out to be equal to plus 1/2. So now what we have is putting in this values of these constants a, b, and c, and using that up here. Okay. So that's equal to 1/2 1 over s minus 1 over s plus 1 plus 1/2 1 over s plus 2. Okay. Yep, that's everything there. And all of that is multiplied by 1 minus e to the minus 10s. Okay. Now we're ready to inverse transform. I could expand this out, but I'll explain how, since we have everything multiplied by 1 minus this exponential, how we can just bypass this, because we can see how it works. So first, transform this part is multiplied by 1. So inverse transform of 1 over s is 1. So it gives us a 1/2. And then over here, the inverse transform of 1 over s plus 1, when it's a shifted linear factor like this, that's an exponential. So anytime you have a shifted function for a transform, I can write the rule down here. So Laplace transform e to the at t. Sorry, I'll get this here in a moment. F of s minus a. All right, so this is a rule I'm using. That here, for instance, I have the function capital F of s is 1 over s. But there's a shift of a equal to minus 1, because I have 1 over s plus 1. So the inverse transform of that, if I go backwards to here, I'll have e to the minus t and then times the inverse transform of 1 over s, the unshifted form. But the inverse transform of 1 over s is 1. So that's all I have for this term here. Same thing in this term. So I have 1 over s shifted with a shift of a equal to minus 2. So that's going to give me an exponential. I have a plus down here and a 1/2, so I have to include that. I have e to the minus 2t. And then after I undo the shift, I have 1 over s, but the inverse transform of that is 1, so that's all I have for this term right here. So all of this times 1 is now inverse transformed. Now I have to account for all of this again times minus e to the minus 10s. But what I can do for that, and I'll fill in the rule here too. Okay. So for this part, like f of s, I know how to inverse transform it. It's all of this, and that gave me this. Um, but because of the exponential, so well, first I'm going to have a minus. I have a minus here, so I need a minus down here. Because I have this exponential in the transform, I'm going to have this unit step function. So that'd be u of t minus c is 10 in this case. And then what I do is whatever function I have that's multiplying all this, so it's all this in the large square brackets here, I'm going to um, transform back to f of t minus c. So in other words, it's a function of not t by itself, but t minus 10. So what I'll have is 1/2 minus e to the, so basically I'm just copying this. But wherever I have t, I must replace it with t minus 10. And then I have plus 1/2 um, e to the minus 2 t minus 10. Be sure to use parentheses for that. Like here we have t being multiplied by 2. But that 2 must be multiplying both the t and the minus 10. So be sure to put parentheses or it'll be wrong. And that's it. That's the end of that example also. Okay. So we've seen certain transforms come up very frequently. So certainly these two rules right here for dealing with exponentials as functions of t and also exponentials of a transform that leads to a unit step function in your inverse transform. Elsewhere, we saw rules for sine and also cosine. Um, so, the, so those transforms that come up in the homework, and those come from various theorems that are featured in the text. And there's the text also features a Laplace transform table. Be sure to have that handy first for homework, and then when you're taking the final, so that you can apply these transforms fairly quickly. Okay, so that'll be it for the semester, except for the final exam. So I'll be recording a video um, next Monday where I will go through the practice final solution.